Hello, grade 12. Welcome to session 4. And don't forget, this is session 4 of patterns, sequence, and series. And today we're going to be dealing with the sum of geometric series. So in the previous session, that was session 3, we were focusing on the sum of arithmetic series. But today I really want us to focus on the sum of geometric series. Okay. Okay, let's look at the content outline. Uh, like I always do, uh, I'll keep on posting this so that you might just have an overlook on what we're gonna be conducting this session, looking at, right? Okay, so in unit 1 we did arithmetic sequences, and that was session 1, right? Unit 2, geometric sequences, that was session 2. Unit 3, the sum of arithmetic series, and that was session 3. So today we're going to be focusing on unit 4, right? Unit 4, where we'll be doing the sum of geometric series. And this is term 1 work. It's on page 15 on your Platinum Mathematics Learner's book. Okay. Okay, great stuff. Unit 4 now. And this is the sum of a geometric series. So, how is a geometric series formed? Very simple. So, a geometric series is formed when terms in a geometric sequence are added together, right? So, if we are adding terms of a geometric sequence together, we can get something called the sum of a geometric series, right? So, there's an algebraic proof below that applies to all geometric series, and they are examinable, right? So they can actually ask you to prove that the sum of n terms of a geometric series, prove that the sum of n terms of a geometric series is a into 1 minus r exponent n over 1 minus r. Or they can say prove that the sum of n terms of a geometric series equals to a into r exponent n minus 1 over r minus 1. So you can see that to calculate the sum of a geometric series, we use two formulas, right? So you can choose any of the formula. It's either you choose this first one that says 1 minus r exponent n, or this one that says r exponent n minus 1. Any of them will give you the right answer, right? So for where r must not be equals to 1. Okay, so I'm just going to show you how to prove this sum. So don't forget, we said a geometric series is formed when we are adding terms of a geometric sequence. So our first equation really will just be simply adding the terms of a geometric sequence. And I'm sorry about the background noise. I can see there's some birds. I'm just outside here, so it's sort of like noisy. Sorry about that. Okay. So we are saying the first equation, we get it by summing up the terms of a geometric sequence. So you just show them while you are summing up those terms. We know that the first term is a, the second term is what? Is a times the common ratio. So you say previous term multiplied by common ratio, you get the next term. So it's AR. When you move, you multiply the previous term with r, that's your common ratio, you get what? AR squared, right? Okay, so we'll add them up until we reach the last term. And I told you that the last term is the same as Tn. So now, because here we're focusing on a geometric series, we'll use the Tn of a geometric sequence, right? So what's the Tn for a geometric sequence? Is a into r exponent n minus 1, right? So if one would like to go back, remember to go in front to get the next term. We just multiply the previous term with a common ratio, that is r. So to go back, what we do really is just to divide with r, right? Just to cancel that r that was multiplied with to get that term, which is the next term. So what I'm gonna do to get the previous term, we're just going to divide with r. So loss of exponents, r exponent n minus 1 minus 1, because I'm dividing by r exponent 1, right? So my previous term will just be a into r exponent n minus 2, because minus 1 is gonna give me minus 2. So this forms our equation 1, right? So that is our equation 1. To get equation 2, very different from what we did on arithmetic series, right? Here on geometric series, to get our equation 2, what we do, we say on our equation 1, we are going to multiply with the common ratio, right? We multiply equation 1 with the common ratio. So then it will be r multiplied by Sn, right? Because we are multiplying equation 1 with common ratio r. So a multiplied by r is gonna give us what? AR. So we'll just write it in the same straight line as the one above. So AR, I'm just gonna put it here so that it might be in the same line as that one above. So it's AR then. Plus, if I say AR multiplied by R, I'm gonna get AR squared. Also, I'm just gonna write it being on the same straight line with that one there. Okay. So if I say ARN minus 2 multiplied by R is gonna give me what? Loss of exponent, minus 2 plus 1 is gonna be minus 1. So I'm just gonna write it being equated to that one there. So it's A into R exponent n minus 1. So if I had moved back again, right, I would have gotten A into R exponent n minus 3, obviously, right? So minus 2 minus 1 minus 3. So I would have gotten, let me write it, A into R exponent n minus 3. So if I take this A into R exponent n minus 3 and multiply it with R, I'm gonna get what? A into R exponent n minus 2. So we are sure that the one that will be equated to that one there is gonna be A into R exponent n minus 2. So and that's how we get it, right? You just move back again, imaginary so, right? And you assume you multiply with R, so you'll get that one. You write it being equated to that one above there. Okay, so then if I say R multiplied by what? By A R exponent n minus 1. So I'm gonna get something like A into R exponent minus 1 n minus 1 multiplied by R. So minus 1 plus 1, they're gonna give us what? 0, right? So I'll just be left with what? With A exponent, A into R exponent n only, because if I add 0, it will still remain the same, right? So this is how we get our equation 2. So, and I hope you understood that. Sort of like a mixed up process, but if you get it, that's it. Okay, so now in proving this formula, very, very different from what we did in arithmetic series, right? So in arithmetic series, we added equation 1 and equation 2. But now here in a geometric series, what we do really is to subtract these two equations, because you can see from the formula there's a subtraction to show that there was a bit of subtraction somewhere. So when you subtract, it depends on which formula you want to prove. So as we want to prove the first part, right? Look at it. It says Sn equals to A into 1 minus R exponent n, right? So check where your R exponent n is. Our R exponent n is in equation 2. So to prove this formula, it means they started with equation 1, subtraction, equation 2, so that we may have that 1 minus R exponent n. So we'll say equation 1 minus equation 2, right? But if they require you to prove this one, so they started with R exponent n. So R exponent n is our equation 2. You were going to say equation 2 minus equation 1. Don't forget that. But as we want to prove this part, that is why we're saying equation what? Equation 1 minus equation 2. So my equation 1 is Sn, and I'm just going to write it here, Sn minus, my equation 2 is Rsn. This is going to give me A minus, you see A has no friend here, right? So we can say basically there is 0. So A minus 0, it will still be A. AR minus AR, AR minus AR will cancel to give us what? 0. AR squared minus AR squared, it will still give us 0. ARN minus 2 or minus AR minus 2, they will cancel each other and they will give us what? They will give us 0 also. 0 also here. But here, let's check here. AR exponent n has no friend, but on top, yeah, there's no friend, right? We can assume there is 0 because there is no friend. So we can say 0 minus AR exponent n, it will give us minus AR exponent n, right? So let's simplify this. So we can see that from here we can take a common factor of Sn, right? When you take the common factor of Sn, we'll be left with 1 minus R is equals to A plus. If you are adding those zeros, they won't have any impact, but there is minus AR exponent n, so it will be minus AR sorry about this, minus AR exponent n. Okay, then you can see that we have a common factor here. Can you see there's a common factor of A? We can take it out. So here we have 1 minus R. There we have a common factor of A. If we take A as our common factor, we have 1 minus R exponent n. So to solve for Sn, you can see we'll divide both sides by 1 minus R. Divide both sides by 1 minus R. This cancel this. And our Sn final answer is gonna be A into 1 minus R exponent n over 1 minus R, where R must not be equals to 1. So this is how we really prove this formula, or we derive this formula for sum of a geometric series. Okay. Okay, let me show you just an example for you to understand this sum of a geometric series. And this is worked example number 1. Don't forget we are still using Platinum Mathematics Learner's Book grade 12. And let's take a look at this example. So worked example number 1, it says determine the sum of the first 7 terms. Very important statement. Of the first 7 terms. So they need the sum of how many terms? 7 terms. N equals to 7 in a geometric series 3 plus 15 plus 75. So what's the formula? The formula says Sn is equals to A into 1 minus R exponent n over 1 minus R. You can use that other one, there's no problem. They will all give you the same answer. From this formula, we must have n, and we have it, number of terms. We have 7 terms that are being added together. Our A is our first term, which is what? Which is 3, and our R is our common ratio, which we get by saying, the following term divided by the previous term. This must be the same as T3 divided by T2. Okay, what is our T2? Is 15 divided by 3. This must be the same as T3, which is 75 divided by 15. They must give us the same answer because this is a common ratio, so the ratio must be common. 75 divided by 15, it's also what? It's also 5. Therefore, we can see that our common ratio is what? Is 5. Now we can get the sum, right? Okay. Okay, let's get the sum. We want the sum of the first 7 terms. Our A is what? Is 3 into 1 minus our R. I told you that every time after a negative, put everything inside a bracket. This is very important because sometimes you get your R as negative, and if you try not to put it in a bracket, you'll make a big mistake. So after a negative, just put everything that follows inside a bracket. So what's our R? Our R is 5. What's our N? Our N is 7, right? All divide by our 1 minus, what is our R? Our R is 5. So we're simply going to use a calculator and determine the answer for this sum, right? So let's do it. So using a calculator, getting 58,593. Right. So when you sum up the first 7 terms, you can see it's gonna get a lot. It's 58,500 and what? And 93. Okay. Okay, let's look at worked example number 2. Sort of like a different type of an example. It's not the same as the one we did previously, because previously we knew n, right? We knew the number of terms that are being added. But sometimes they won't give you the number of terms, they will just give you a series and they say determine the sum. So they said determine the sum of the terms in the series 5 plus 10 plus 20 plus 40 plus up until we are adding to what? 655,360. So what is our 655,360? It's our last term. So this is our last term, right? It is our last term, and I said the last term is the same as what? STN. Don't forget that. Last term is the same as TN. So what's the formula of the sum? It says Sn equals to A into 1 minus R exponent n over 1 minus R. We must have n, we must have A, which is our first term, we can see is 5. We must have the common ratio, which we can get by saying the following term divided by the previous term, the following term like that, divided by the previous term. So I'm gonna substitute those things and see how it goes. Term 3 is 20 divided by 10. 10 divided by 5 is 2. It's 2. And 20 divided by 10 is also 2. So our common ratio is what? Is 2. But we don't have n. We don't know how many terms are being added, right? We are just given the last term. So it's our duty to go and calculate n. So we are given the last term. It's going to be easy to calculate n because we know the last term is the same as tn. So our tn is going to be 655,360. But we know that the tn of a geometric sequence is a into r exponent n minus 1 is equals to 655,360. What is our a? Our a is 5. What is our r? Our r is 2 into n minus 1 is equals to 655,360. So to solve for n, I'm going to divide both sides by 5, right? When we divide both sides by 5, it's going to be 655,360 divided by 5. Then we'll be left with 2 exponent n minus 1 is equals to 131072. So to solve for n, we have to raise this to the same base as this one, right? So its base must be 2. And I showed you on the previous video, if you check session 2, when we did a geometric sequence, I showed you how you can raise a number to the exponent of, to the power of the same base. So you just punch the number 131072, you punch equal sign, then it will appear again. You press shift, then you press fact, just a button below the letter B. So it will show you 2 exponent 70 if you are using a Casio calculator. So it's n minus 1 is equals to 2 exponent 70. So now the base are the same, we can equate the exponent. So n minus 1 is equals to 17. Our n is equals to what? 18, right? When you take 1 to the other side. So now we have all our unknowns. We have all these things. Now we can go and calculate what? The sum, right? Okay, let's go and calculate sum. With n equals to 18, it shows that they were adding how many terms? 18 terms, right? So don't do that silly mistake of just coming and calculate here. You see 1, 2, 3, 4, 5, and you say they are adding 5 terms. Very incorrect, because here they are showing you that this addition is still continuing, but we are just showing you that it will end here. This is the last term, so there are still some terms in between there. So it's 18 terms that are being added. So sum of 18 terms, our a is 5, 1 minus r is 2, exponent n, which is 18 over 1 minus our r, which is 2, right? Just simply use your calculator and get the final answer. So the final answer is gonna be 1310715. You can see this sum is a lot, right? It's a lot. It's 1, 2, 3. It's 13,000. Is it 13,000? 1, 2, 3. Sorry, it's 1.3 million and all that. So it's a lot. So that's really how you calculate the sum, right? So this is the sum of a geometric series when you are given the last term but you don't know the number of term. What you do, you first calculate the number of terms, then you go and calculate your sum. Very simple. Okay. Okay, let's just take this time to just give you a fun activity so that to help you to engage in this session, and let's see who can get this one. Just pause the video and read the question and try to answer it. Drop your answer on the comment section, and I'll comment and tell you if you're correct from there. Okay, the question says the first term of a geometric series is 16 and the sum of the second term and the third term is 12. So the question says determine the sum of the first 10 terms. Right. Pause the video and just try it by yourself and just drop your answers on the comment section. Then we'll take it from there. Okay. Okay. Welcome to this really interesting part of this session, and this is that part that gets you really thinking, is this really possible? Can we really calculate this? So sum to infinity, and it's when I first introduced to this, I was asking myself, is it possible? Because infinity, we can't reach infinity, but mathematicians here are just saying no, no, no. You can actually get the sum to infinity, and and you'll be very surprised to how they actually got this. So they use a method, right? So they use a certain method, and they're saying, okay, if our terms in a geometric sequence are approaching 0, right? So if they are approaching 0, then we can actually predict really or calculate the sum of infinity, the sum of all the terms that will be there, right? So there's no limit of the terms that we are adding, but we'll just be calculating all those terms that's gonna be in that sequence. So sum to infinity, you don't have this in an arithmetic series. Very, very important. You don't have sum to infinity in an arithmetic series. So sum to infinity, that's why I'm putting it here in a geometric series, because you can only calculate sum to infinity when the terms are of a geometric sequence, right? So let's see what is sum to infinity. So you can see that it's a sum that we calculate where there's no limit. There's no limit to the number of terms that are being added to determine that sum. So we call it sum to infinity, right? So there's no limit. They're just saying calculate the sum, and you then have the last term in a geometric sequence, only in a geometric series. So we can actually calculate this sum to infinity. Keywords. So now you get some of the properties of this sequence or of this series, how it should be. So it must be an infinite series, right? So we have two types of series. We have an infinite series, and we also have a finite series. A finite series, right? So with an infinite series, it's a series that has no end. So we don't have the last term, right? For which it is impossible to determine the number of terms, right? So if we don't have the last term, it's impossible to say how many terms are here. So you are just adding things. They are going infinite. That's why it's called infinite, from the word infinity. No end, right? So very, very important second characteristic. You have to determine the sum of infinity only. You can only determine the sum to infinity when your series is convergent. And these are some of the new terms, and I would really explain it as we are continuing this series. What do we mean when we say the series is convergent? What do we mean when we say the series is divergent, right? So we have also two types of series. In a geometric series, they can be convergent and they can also be divergent. Now I'll only explain the one for convergent. So for convergent, it is when your Tn is 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 moving closer to zero as n increases and becomes more bigger and bigger. As your n is increasing, you find your Tn is moving closer to zero as n is approaching infinity, right? As n is increasing 1 2 3 4 5 6 7 8 200 500 like that 1000. As your n is increasing and it's approaching infinity, you find that your Tn in that series is getting closer and closer to zero. Then we say that series, that geometric series, is what? Is convergent, right? So there are some of the things that you can see or that you can calculate to see if your series is convergent or not, right? So you simply calculate your R. So if your R is between -1 and 1, then your series is what? Is convergent, right? So now this is a condition. If your R is between -1 and 1, we say the series is convergent. And your R exponent n, let's say for instance my R exponent n is my Tn, right? Let's take this as my Tn, where A is 1 and we have now 1 into R exponent n. So as my Tn, if it's moving closer to 0, as n approaches infinity, then we can get this sum of infinity. Why? Because those terms will be moving very closer to 0. They'll be becoming very small, right? So even if you are adding them, they won't have that much impact on the sum. So it's easier now to determine what? The sum to infinity, right? So let me just explain also really about this convergent series. Let's say for instance your R is 1 over 2 and your sequence is 1 over 2n. This is your sequence, right? So this sequence will be convergent because our R is between what? Take a look at here. It's between -1 and 1. If R is between -1 and 1, the series is convergent. So if my Tn is 1 over 2 exponent n, and I'm increasing my n, let my n approach infinity. So if my n is increasing, let's start from 1. N equals to 1, I'll get 1 over 2, right? 1 over 2, which is 0,5. So if my n increase now and becomes 2, right? You can see my n becomes 2, I'll get 1 over 4. And 1 over 4 is what? 0.25. So 0.5, then we move 0.25, then 1 over 8. 1 over 8, if n equals to 3, 1 over 8 is what? 0.125, like that. You can see that as we are moving, as n is going towards infinity, your Tn is approaching what? Is approaching 0, because these numbers are decreasing closer and closer. They are getting closer to 0. So in order to determine their sum, it's going to be very easy to get the sum to infinity, because as they are moving closer and closer to 0, those other ones that are far away closer to 0, as we are adding them, they won't have much impact on the sum, right? So now mathematicians said, okay, well, it's easy. We can really get this sum to infinity, and if we have this kind of case, right? So that's how they actually come up with this thing, sum to infinity. So the symbol to represent the sum to infinity is this one, S, and this one. So this one is the symbol for infinity, right? So they just use that thing. It's like an 8 that is sleeping, 8 that is sleeping. So this is the symbol that they will use in order to say this is the sum. S stands for sum to infinity. So let me show you how they prove the formula for the sum to infinity, although I've already explained this. So notice that your R, if you want to calculate the sum to infinity, there are conditions. The first condition is that you must have obviously infinite series, right? where you don't have the last term, you are adding the terms continuously like that without the last term. Number 2, the series must be convergent. That is, your R must be between -1 and 1. So after that, this is the formula for sum to infinity. Say sum to infinity is equals to A over 1 minus R. So this is the formula. How do we prove this? Because we will be adding terms of a geometric series. How they actually find this formula? They used one of the formulas for calculating the sum of a geometric series, and the formula they used, according to this 1 minus r, we can see that they use a formula that says Sn equals to A into 1 minus r exponent n over 1 minus r, right? So from this formula they are saying, let n approach infinity. If n is approaching infinity, then r exponent n will be moving closer to what? To 0. Because, and also another condition, okay, let me start with this one. Let n approach infinity, right? Where r is between -1 and 1. Where r is between -1 and 1, then you'll find that your r exponent n will be moving closer to what? To 0. So what they did, they just replace r exponent n by 0, and they replace n by infinity because they wanted to calculate the sum to infinity there. Then they replaced, then they got a times 1a over 1 minus r. So that's actually how they got the formula. Very important, you must know the condition. The series must be convergent. R must be between -1 and 1. As n approaches infinity, is moving closer to infinity, your r exponent n will be moving closer and closer to 0. Then you can replace then you prove that formula. Very simple proof. I don't really need to write many things here. So that's it, right? Sum to infinity. Okay, let's take a look at an example to really show you how you can calculate this sum if they give you. Okay. Work to example 1, sum of infinity. So determine the sum of infinity of the sequence 16 plus 8 plus 4. You can see the 3 dots there. They are saying they are summing up to infinity, right? So like we said, sum to infinity, the terms there, they are of a geometric series, not arithmetic series, right? So the terms are of a geometric series, right? So sometimes you won't be told that this is a sum to infinity. You have to think for yourself. They can just give you this series, adding the terms together. Ish, there's a bit of noise here. Let me just move first. Okay, I'm saying sometimes they might not actually tell you this is a sum of sum to infinity. They can just give you the terms of an arithmetic series, and they just say determine the sum of this series, right? So you must be able to know. For example, if I'm given the last term and it's a geometric series, I know we'll have to use those formulas that we've been using previously. But then if it's a geometric series, there's no last term and they don't tell us the number of terms, they just say determine the sum. So the terms are just going to infinity, so we'll calculate sum to infinity. So this example is it's basic. They just tell you determine the sum of infinity, so it's simple for an infinite number of terms. So we know the formula for sum to infinity is the same as A over 1 minus R, right? Okay, so where our A is our first term, which is 16, and our R is our common difference, our common ratio, which we get by saying the second term divided by the previous term, the third term divided by the previous term, right? So second term is 8 over previous term 16. Third term is so about this 4. It's 4 over 8, right? So this is 1 over 2. Also this side is 1 over 2. So your R is 1 over 2, right? So we can go and get the sum to infinity. Very simple formula, A over 1 minus R. Our A is 16 over 1 minus. Our R is what? 1 over 2. So ensure that after every negative sign, put whatever follows in the bracket, right? To avoid making mistakes. Because most of the learners have I've been making mistake on this problem for sum to infinity, and you guys just think maybe this is a simple thing, the formula is easy and all that, but you can make those silly mistakes. For example, if r is minus 1 over 2, most learners can write sum to infinity is equals to a as 16, 1 minus 1 over 2. This is wrong because your r is negative. So negative and negative, it has to change to be positive. That's why we really advise you when you are writing sum to infinity and all that, all those other problems, if you are solving for x and all that. So just write after every negative sign, put everything in brackets to avoid making mistakes, right? Then we can get the answer 16 over 1 minus into 1 over 2. It's going to give us 32. So this is the sum to infinity. When you add those terms to infinity, you will get approximately 32. Why am I saying approximately? It's because really, it's not really possible to determine the sum to infinity, right? You just approximate. Even this formula was just approximated and estimated that, okay, as we move to infinity, those terms move closer and closer to 0. They will be very, very less. So it won't have much impact. So so this will be your answer, really. So sum to infinity, 32. Okay. Okay, let's quickly sum up this lesson by just talking about these two concepts, because these are one of the questions that you'll always find in your grade 12 final exam paper, trial exam, your term 1. This question is just always there. They can say, is this series convergent or divergent? Give a reason for your answer. So you must know what is a convergent series and what is a divergent series, right? We already talked about convergent when we were talking about sum to infinity, and we said for convergent, it's when Tn it's moving closer to 0 as n tends to infinity. That is, as you are increasing n, your Tn will be moving closer to 0, right? So how do we know that our series is convergent? You calculate r. Also, how do you know that it's divergent? In these situations, if you get this question, is this series convergent or divergent? Give a reason for your answer. What you do, calculate the common ratio, R. After calculating the common ratio, you just need to know the condition for convergent, the condition for divergent. So if your R is between minus 1 and 1, as you can see there, if it's between minus 1 and 1, the series is convergent. What does it mean? Let's come to the understanding part, not this just to memorize it's between minus 1 and 1, it's convergent. So for understanding, this means that if your R is between that interval, minus 1 and 1, mostly it's a fraction like that, 1 over 2. And if your Tn is 1 over 2 exponent n, and you'll be increasing your Tn, right? I mean, you'll be increasing your n moving to infinity like that. So if n is 1, 2, 3, 4, 5, you find that these terms here, right, these Tn's here, they tend to move closer and closer to 0. They approach 0. So we say they are converging. So it's a convergent series. Do you understand? Okay, so let's talk about divergent. What about divergent? If you want to know if your series is divergent, also you calculate r. So your r must be greater than 1, or r, or you can get your r as what? As less than minus 1. If your r is greater than 1, that is your r 2, 3, 4, 5, 6, 7, 8, like that. R less than minus 1, minus 2, minus 3, minus 4, like that. Then what? Then it's a divergent. What does it mean when we say it's a divergent? Tn grows further apart in value. So those series will be growing further apart. Let me take a look at this example here. If maybe our r is 2, we know that our r is greater than 1, right? And we have a general term as 2 exponent n. It's divergent. Why? If you put 1, as n tends to move to infinity, as n is growing, your values are moving apart from each other. They are not moving closer to 0. They are diverging. They are moving away from each other. So we say the series is divergent. But in simple terms, you just calculate r and you check your r. Is it less than minus 1? Is it greater than minus 1? Then it will be what? Is it greater than 1? Then it will be divergent. For convergent, also you calculate your r and you see if your r is between minus 1 and 1, it's convergent. So if they give you this question, is your sequence convergent and divergent? Calculate R, and after calculating R, sometimes they can say give a reason for your answer. Why are you saying it's convergent? Maybe you calculate R and you get R is 1/3. So we know that the sequence will be what? Will be convergent. Why? Why is it convergent? Because my R is between -1 and 1. So the reason that I'm going to give them is that 1/3 is between -1 and 1. So that's the reason you give. You don't write words that R is between what, and for convergent they are moving. No, no, no. Just write this mathematical symbol. R is between -1 and 1. That's why we're saying it's convergent. If it's divergent, it's either you got your R being greater than 1 or R, sorry about this, or R being less than -1. Okay. Okay, let me just show you this quick example and we will just call it a day for today. So it says consider the series. Very important question. These are those questions that you have to expect them in past papers and all that. They're just there. They can use X, they can use anything. So consider the series for which values of K, value of values of K, of which will the series be convergent, right? For which value of values of K is this series convergent? What do we know about convergent? If our series is convergent, our K, our R must be between -1 and 1. So that's the condition. So we have to calculate R, right? And we see. So our R will be second term divided by previous term, like that. So this will be 8k squared divided by 16k, right? So it's 8k times k, like that, divided by 16k. 8 divided by 16 is 1/2. Then k cancel, will be left with k/2, right? So our R is what? Is k/2. So if you want to solve for which values of k will the series be convergent, what you do, you substitute your R where there is the condition for convergent. So we're gonna go back here and we're gonna substitute our R, which is k/2 must be between -1 and 1. You are not done, right? They need the value of k. For which values of k? So you have to solve for k. Up until here in the middle you have k only. So you have to think of how do you solve inequalities. So to solve this, we can multiply all sides by 2 so that 2 and 2 cancel each other. So it will be -1 times 2 less than k/2, multiply by 2 less than 1, multiply by 2, right? Then it will be -2 less than 2, cancel 2, we're left with k. 1 times 2, 1. Is 2. So for which values of k will the series be convergent? It's only when k is between -2 and 2. So that's it. Okay. Okay, great stuff. Thank you for joining me today. Thank you for watching, and this marks the end of session 4, where we were focusing on the sum of geometric series. First 2 examples mainly on geometric series. Then we move further. We are still on geometric series. Then we talk about sum to infinity, convergent and divergent series, and how we can calculate those. Okay. Thank you very much for watching. And enjoy the rest of your day. Thank you and goodbye.